So welcome everybody. It's been a long time. And I'm going to talk about computer science today. So why am I going to talk about computer science? Well, I know from personal experience that a lot of people who are working in software didn't study computer science. And that's great, because you know that diversity of thought really makes things better. I think stuffy old white guy can come up with a number of things, but if we have more people, we can come up with better things, and that's great. But computer science is also important, and sometimes I notice that people don't know certain things, which I got to learn when I studied computer science, and they can actually help make your life as a software developer better. So I'm going to teach you those things in a little under an hour, and then you don't have to study computer science anymore. So that's great, right? So if you remember only one thing, it's the next thing. After that, you can zone out and still have learned something. It's this, the Morgan's laws. That basically means, well, let me make it a little bit more understandable. It's a way to rewrite your Boolean expressions to make them easier to read. So for example, say you have this piece of code. To actually understand what this Boolean expression does, you have to think about it a little bit. But we can rewrite this. So let's pretend that the one part is A and the other part is called B. Now we have a formula that looks like what we had before. So we can shuffle it around according to the rules and put them back. And now simplify a little bit more, and your expression is a lot easier. So if you remember this, then you are already ahead of the game. But how do you know that is actually true, what I'm saying? Well, you can put those things in a truth table. So you put all of the values in there. 0 is false, 1 is true. And then you just do the math, basically. A or B, and then not. What does that end up for each of the possible values? You can do the AND version as well. You get this table. So if you only remember two things, truth tables can really help figuring out your Boolean expressions. It's a really nice tool to use sometimes. So my name is Jan. I work at Yoink, a small consultancy here. We're hiring. I also wrote equals verifier. You can find me on the interwebs. And I studied computer science, so you don't have to. So computer science, it's the science, but it's also the people. And the people are actually more interesting than you would think for such a stuffy subject. So let's talk about those people as well. For example, we have Edsger Dijkstra. That's the Dutch computer scientist, the most famous one. He invented the shortest path algorithm, for example, that you can use to find your way using Google Maps. So, pretty important. But he was also very quotable. He said things like this, like testing shows the presence and not the absence of bugs. And I don't know if anybody was at my Ignite talk earlier, where I said that my first language was BASIC. Oh, that's the next quote, actually. The teaching of BASIC should be rated as a criminal offense. It mutilates the mind beyond recovery. I think I still turned out pretty okay, but who am I to judge? And he also wrote papers that you can read on the internet, like why numbering should start at 0, and it's actually a pretty entertaining read. You can just look that up. It's fun to read. He always often wrote with pen. But he stood at the basis of my computer science curriculum in Eindhoven. And one of the first things that we learn here is this. You have a precondition, which is some Boolean expression, which you assume is true. Then you run a statement, and then after that, the postcondition is true. So, very simple example. If x is 3 and you increment it by 1, then the postcondition is that x is 4. Pretty straightforward. So, QED. If you apply that to a simple algorithm, so this is searching something in an array. I've written it here in Java, but we used to write it like this in Eindhoven. You got preconditions like this, and this means that we assume that the thing I'm looking for is somewhere in my array. And now I assume still the same thing, but also I equals 0. Now inside of the loop, we have a condition that's always true, which means here I is in range. We still haven't found the thing, but we know that it is still in there. That's what this expression means. And after we increment I, then we have to update all of the less than and equal symbols, but it's basically the same thing. And at the end, we know that I is somewhere in range of the array, and also we have found the value that we were looking for. So this is what computer science looked like for me. And this was, you know, we had to do it with pen and paper, and this was kind of what it looks like. And you can forget about all of that. I mean, proving algorithms is hard, and almost nobody ever does that, and there's actually a good reason for it, which I'm going into next. So first, let's speak about algorithms a little bit. This is also a very famous guy. I don't know if you can read the name. Maybe this is a little easier. Muhammad al-Khwarizmi. And in Latin, his name would be Algorithmi. And that's where the word algorithm came from. Also, there's a crater on the moon named after him and other cool things. So about algorithms, these days we live in an age of libraries, which means you can pick a library and the algorithms are already in there. So when you have libraries, you don't have to implement an algorithm, you don't have to prove it, you don't even have to test it, you just have to choose one. Because it's in a library that you can choose that's probably already there. So how do you do that? Well, you can have somebody do it for you. And this happened also in reality. This is Katherine Johnson. She was working at NASA for the Apollo programs. And what she did was, when the computer would have calculated the trajectory of the rocket that took people to the moon, she would, by hand, do the same calculations again to make sure that the computer didn't mess up. And the astronauts actually didn't trust the computers, they only trusted her to do these calculations. So if she didn't do them, they wouldn't go on the rocket. They just refused. Think about that today, right? And that was actually, you know, a cool story. They made it even into a movie. But let's talk about these algorithms. How do you know which one you have to choose? Well, the first thing that you have to know about that is complexity. How many steps does it take to execute my algorithm? So let's say that n is the input size of the thing that you want to calculate. What would be the complexity of an algorithm? So here is an algorithm, linear search. You just go through a list and until you find the thing that you were looking for, and the complexity of that is n steps, so the input size. So if your array contains 10 elements, then we would often do around 10 steps to find the element in the array. But if you know the index, then you only need to do one step, so the complexity is one step. There's other algorithms like complexity, finding duplicates in two distinct lists. You have to iterate over each of those lists. So now the complexity becomes n squared steps, n times m. Fibonacci famously is 2 to the power of n, so that's a big one. I don't know if you're familiar with traveling salesman, but that one is also very large. It is n faculty, so that it means if the input size is 3, you do 1 times 2 times 3. Then there are things like a binary search, or if you use Git, maybe you're familiar with Git bisect. That has log2 n steps. What the hell does that mean? Let's just say it means this, right? That's all you need to know. So this complexity is interesting, but you know, on its own, it's not very useful. So let's go one level of abstraction higher. And let's talk about Donald Knuth, also a famous computer scientist. He said things like, beware of bugs in the above code because I have only proved it correct and not actually tried it. He was also the guy who wrote checks for people who would find bugs in his code. So the first person to do so would receive a check of 1 cent, and then the next one 2, and then 4, and then 8. And somehow he never got poor because of it. Because, well, first of all, he didn't make many bugs. But second of all, when people would receive one of his checks, they would, frame it and put it above their bed instead of cash it. He's also famous for this quote, which is often misquoted, actually. This is the full one. A lot more nuanced than the famous piece that everybody knows. But who cares about that? He wrote this book, and in this book, he talks about the big O notation. So if you have a complexity of a certain number of steps, then you could write that down in the big O notation. So if you have one step, you say big O of 1. If you have n steps, you say big O of n, etc. But the funny thing is that if you have twice n steps, 2 times n steps, then we still say big O of n. And if it gets more complicated, we just pick the biggest n that we have, and that's the big O. And that makes it easy to reason about these algorithms. Because if you have a small big O, then it doesn't matter if you have only a few elements in your input size or a lot. It doesn't grow very much. But if you have a large big O, then it can grow, the number of steps can grow very, very quickly. So if you have an n faculty algorithm, then, good luck finding a solution to your problem. If you put it in a graph, it looks like this for the visually oriented people. And we also have given names to the most common big O instances. So like a linear algorithm is one that grows with the input size, and a quadratic one that grows quadratically with the input size, etc. We also made a division. If n is not in the exponent, or if the exponent is just an integer, then we would call it a polynomial algorithm, and otherwise, we got a little lazy with the naming, so we call it slow. And this is an important distinction. So why do we care about this distinction and this big O stuff? Well, Alan Turing is an example of a computer scientist who cared about this because he had to crack the Enigma codes in the Second World War. Unfortunately, he led a very tragic life because he was also homosexual, and that was not allowed in England at the time, and finally he even committed suicide, which makes for a good movie, but for a very sad life. So that's very unfortunate. I wish things would have turned out differently for him. But he cracked those codes. And here's a disclaimer: I'm going to simplify things from here on, just so you know. So cracking codes, if you have an encoded piece of information and you want to crack it, then the algorithm to do so will have a complexity that is worse than polynomial, or it will have a very large big O. But if you have a solution or a possible solution and you want to check if it is actually correct, then the algorithm to do that is polynomial. And polynomial means basically you can reasonably execute this algorithm and still live before the computer comes back with an answer. So this is a thing called NP, non-deterministic polynomial. You can forget about that word immediately, but it means all of the problems where finding an answer is very slow, but if you have an answer and you want to check it, that is very fast. And this comes up in practice a lot, like solving a Rubik's Cube or doing logistics for a big supermarket. And even parts of Bitcoin are NP. And of course, we assume that polynomial algorithms and NP algorithms are different classes. But the funny thing is, we don't know for sure. Nobody has ever proven that it is the case. We just assume that it is. We haven't found any evidence to the contrary, but we assume it. And this is actually kind of funny if you think about encryption depending on the fact that P is not the same as NP. So if anybody ever manages to prove that those two classes of problems are the same, you can either collect the prize money of $1 million, I think it was, or just, you know, decrypt all of the transactions on the internet and steal money that way. So what can you do with this in practice? Well, here is another computer scientist who did a lot of practical things, Grace Hopper. She invented the COBOL language, for example. She was also an admiral in the US Army, in the US Navy. And she invented the word bug because at one point one of her programs didn't work correctly, and they still had these machines where you had to plug in cables into slots, and they found an actual bug causing a short circuit in the machine, and that caused the malfunction. And she put the bug, she taped it into her notebook, and now the notebook is in the Smithsonian because that was the first bug. So in practice, it helps if you know the big O of the algorithms that you use in your program, and also that you know the data structures that you use, because the operations on those data structures all have this big O thing attached to them. So let's talk about arrays. This is a piece of computer memory, and an array that is contained somewhere in that memory. And all of these places do not belong to the array. Now, if we want to add something to the array, we can just, you know, put it right there. That's easy. So if we look at the big O, we've seen before that accessing a specific index in an array takes only one step, so that has a big O of n. But searching in it has a big O of, sorry, the accessing has a big O of 1, searching has a big O of n, and we just saw here that appending something to the array has a big O of 1. But prepending, if you want to put something at the beginning, then you have to shift everything one place up. That has a big O of n. So if you have a linked list, which is a different kind of list, that kind of looks like this. You have a cell with a value and then a cell with a pointer to the next value. If you want to prepend something, it's very easy. You just, you know, create a new cell and point to the first one of the old list, and then you're done. So prepending has order 1, but access now is actually slow because if you want to index a certain value, you have to traverse the whole thing. So this list has different properties and different performance characteristics. Same with hash maps. I don't know if everybody knows how a hash map works internally, but what you do is you take a value, you calculate the hash code, then you take, well, in this case, basically the last digit of the hash code, and that's the bucket in the hash map that you put the value in. So if you want to add another value, you just calculate the hash code and find the bucket and add it there. That's how a hash map basically works. And for hash maps, access and search is basically the same thing. It has O1. Iteration, of course, it has n elements, and if you want to iterate over all of them, that has On as well. And inserting is very easy, it also has O1. So if you use Java, there's lots of data structures to choose from. These are a couple of lists that you can use, and they all have their own properties and characteristics that you could know about. Except for vector, nobody uses vector. Same thing for sets. Same thing for hash maps. There are even other data structures out there like queues and dequeues. And if you are willing to import a library, you can also go immutable if you want. So all of these things have their own characteristics. And sometimes in Java, you want to be able to swap out, you know, the implementation because you want to have different characteristics. So instead of this, you would write this. And now you are free to change the implementation without the rest of the code knowing about it. But you know, hey, I'm using a different kind of list, so this works differently in my situation, and that's what I want here, or not. And there are other types that you can choose. So Margaret Hamilton, also working at NASA, at the time programming was seen as a glorified typist job, so a lot of women in those days. Somehow men, I don't know, took over for some reason. But in this time, Margaret Hamilton wrote the code that guided the Apollo missions to the moon, and when she printed out the code for that, this was the stack of paper that it produced. And this was such an iconic photo that even Lego made an official minifig of this. So that's cool. And an important thing about her is that she came up with the term software engineering. So what is software engineering? Well, it's a bunch of practices thrown together. So you have programming, obviously. You have these kinds of things. And I think computer science is one of those things. And it's not the most important one by far, but it is in the mix there somewhere. But if you only remember 3 things from this talk, the important thing to know about software engineering is if you have a question, the answer is always this. So with this big O stuff, you know, it can be very important to choose the data structure that you need. But if you know that your algorithm will never exceed some certain, you know, accepted boundary, you don't have to care about it. You know, you can take a data structure that is not the optimal one, but it doesn't matter because your program will, if you run your program, you might not notice it. And that can simplify things a bit again. Or if you only have a couple of values, then you can, you know, spend hours finding the best data structure, but if you just use an array list, it will probably be fine too. And that helps with readability also, because, you know, I have decided that a linked hash set is the best implementation for what I'm trying to do. But if you start using that, then people reading your code will start thinking, hey, what the hell is that? What does that mean? But if it, you know, if you can use a set because you only have a couple of values in there and it doesn't really matter, then it makes it a lot easier for your coworkers. So wrapping up, let's talk about Tony Hoare. He is famous for this quote. He came up with the null reference, and he calls it his billion-dollar mistake because null pointer exceptions, debugging them, has cost so many developers so many hours of their working lives. It has probably cost $1 million or $1 billion. So he kind of regrets that decision now. But he also came up with this thing that I showed earlier. It's called the Hoare triple after him, the precondition statement, postcondition thing. So recapping, if you remember only one thing, it is the Morgan's laws, the Boolean rewriting. And at the end, I'm going to give you a link to this presentation so you can look it up. Or, you know, it's also on Wikipedia, of course. The other thing that you should remember is truth tables. If you have a complicated Boolean expression, you just, you know, write a truth table, and you will figure out what it means. We've talked about complexity and big O. You know, if you're writing something, it helps to know these things to choose the right thing. And again, know your data structures, know what is available, know what you can use and when you should use it or when you should not use it. And the third thing, of course, it depends. Always depends. And that's enough computer science. So where do we go next? Well, the thing is, you know, keep this stuff in the back of your head, not in the front of your mind, because you can always look it up when you're in trouble, when you need it. So here's a tip. Google that, and that's helpful. If you think, well, this stuff is actually quite interesting, I want to know more, then this is a good book that I recommend. It's, you know, most books when I studied computer science were very boring and stuffy, but this one is actually pretty nice to read. I see some people taking pictures, so I'm leaving this up for a moment. Okay, and what else? If you think this book was cool and you want to go even further, well, you can experiment a little bit, you know. Try implementing your own HashMap or even your own compression algorithm if you're really into it. That's been a cool exercise that I had to do when I was in university. You learn a lot from that. So that's it. Are there any questions? I see people scanning the QR code, but I see no hands raised. Well, then that's it. Thank you very much.